All right, how's everyone doing? Yay. All right, questions from what we've been doing? Yeah.
I'm really confused on PA5
Okay.
for the in between 1 and the 4 count.
Mm-hmm.
I'm not sure how to start that. I have...
To start coding it, or
Yeah.
trying to understand it? To code it. Okay. Go ahead.
So I have a main function done, I think. I'm not sure, because that's obviously a loop, right?
Right.
Would that be in main? Would that be in the egg function?
That's part of the egg function.
Okay. So I've got that right.
Okay, good.
And then I've got everything except for the minimum stuff.
So pseudocode. So we do some stuff inside this loop. We call egg on f minus 1, eggs minus 1. We call egg on floors minus f comma eggs. We find the largest of those two. We add 1. Okay. So this stuff in parentheses that we're asked to find the minimum of, I'm calling that a. Okay. And we want to find the minimum of this across all the values of f. Okay. So here's one way to do this. So if f is equal to 1, first time we're going through, we just set our best answer to whatever answer we got. That's the first value that we calculated. And then we say if a is less than best, then set best equal to a. A is the best answer. All right, so that's like a running sum, but it's a running minimum. So basically each time through, compare your answer to the smallest answer you found. If this answer is smaller, remember it. Right? And the only trick I'm doing here is the first time through, I always remember that answer, rather than setting a to some huge number like infinity. So does that make sense?
Yeah. Is a what you put into the array?
A would be the value of egg, floors, comma, eggs, right? It's the minimum over all those values of f. So, so then when you're done, that's the answer you're going to return. And yeah, before you return it, save it in your array.
Okay. F is just like a temporary variable. Like
Yeah. It's just an iterator for going from 1 to floors.
Thank you.
Mm-hmm. So other questions? All right, everybody turn in their SLP. Template upload. Awesome. So I will send those to the printer this afternoon, and I'll have your posters for you next Tuesday for the presentation. All right, so let's talk about a new data structure. This is something called a trie. And it's kind of like a tree, and there's some folklore about why it's called a trie, but I don't know what's true. A trie is a very wide tree. It's a tree where your nodes look something like this. So depending on what you're storing in your trie, your nodes are wide enough to store a number of things. So I want to think about a particular case where we're only storing words with uppercase letters. So no spaces, no punctuation. We're only storing words containing just uppercase letters A through Z. And we're going to have a root of the tree. And our empty tree is null. So let's say we want to store one word. Let's store the word cat. Okay, so here's the root node. I'll go with my picture. Let's store the word cat. Okay, so here's what we're going to do. Here's the root. The first letter of cat is C, so we're going to put a node underneath this pointer, right? This is 26 pointers, pointing to 26 nodes. Everything that I'm not showing an arrow from is null, okay? So all of these are null except for C. C is going to point to a child node. And in that child node, A, the first pointer, is going to point to another child node. And in that child node, T is going to point to another child node. And in that child node, end of string is going to be set to 1. So this is just a bit, and it's going to be 0 everywhere. And all of these pointers are going to be null unless I show otherwise. So these pointers are not null. They're pointing to other nodes, and this EOS bit is set to a 1. And this is now a 26-way tree that stores the word cat. And now if we want to store the word dog, we'll take a pointer from this D node and point it to a child, take a pointer from the O, take a pointer from the G, and then set this end of string to be a 1. So we got a cat, we got a dog. Let's store cats. Okay, so we start off with a C. That's already pointing to a child. We go down to the A. That's already pointing to a child. We go to the T. That's already pointing to a child. We'll go to the S. We'll have that point to a child node. And then we'll set the end of string equal to 1.
So is that now storing both cat and cat?
It's storing both cat and cats and dog. So let's store the word car. So we'll start off with C, that's pointing down here. There's an A that's pointing down here. R is null, so we'll have R point to a new child node. And then we'll set the end of string equal to 1 in that. So we have 4 words stored in this structure. So if we want to find a word like cat, right, take the first letter. If that's null, the word's not in the trie. If it's not null, follow it to a child node. See if that node has a pointer coming off the second letter, A. If it does, follow that to a child node, see if that has a node coming off the third letter, T. If it does, see if the node that it points to has end of string set. If it does, then that word's contained in the try. So if we search for cars, we'll start off with a C, come down here, follow the A, come down here, follow the R, and then we will come down here and try to follow the S. The S is null, cars is not in the try. Get an idea what the mechanics are? So how efficient is this? Like time-wise?
The ON, or N's length of the word.
Yeah, it's basically ON, where N is the length of the word. So if you're looking for a word that has 5 letters, it's going to take you at most 5 or 6 operations to find the word or decide that it's not in the structure. So really, really efficient. It's not a function of how many words you have stored. And you could have a zillion words in here, and if you want to find the word cat, it's, you know, follow 3 pointers and look for an end of string bit to be set.
Would this be functionally how you would store dictionary words?
You could.
So I've heard people use the hash table as an example, but it seems to have some advantages to that.
Hash tables, you know, are theoretically order 1, but you have to deal with collisions. If you can do the legwork to find a good hash function and a good way to deal with collisions, hash tables are very efficient. What's the big downside of tries?
Tons of space.
Tons of space, right? Each of these nodes is, you know, 26 times 8 bytes, plus, you know, an extra byte for the string there. That's a lot of storage per node, and most of that space is wasted. Most of these pointers are null, right, but they got to come along for the ride. So we're really way off in the time efficient, space inefficient part of our design graph. I don't know where tries are actually used in practice. I love them. I coded tons of them when I was in school because it was just kind of like something fun about it. It's so sort of heavy-handed. So inserting is, you know, fixed number of operations. Searching is a fixed number of operations. Now deletion is tricky. It's hard to delete from here. We can just clear an end of string bit, but it's hard to delete in a way that lets you reclaim the space. Right? For example, if I got rid of you know, whatever word was in here, I think that's car, I should be able to free up this node, right? And that's a little harder to do. But if you're just throwing things in, or if you're just building a static database and you just want to go through and search it, this is nice and efficient. All right. Well, let's play with these. So let's pair off in like groups of 2 or maybe 3 if there's an odd number. And let me pass around some of these worksheets. And let's just go ahead and put some things into here and make sure this is making sense.
Did you put this?
Okay, so let's go ahead and let's insert ABC into the try. So take the first thing as being your root node, and then you can create other nodes however you like.
So, if you had if you had like cats in your try first, and then you wanted to add just cat,
Mm-hmm.
you just added end of string at the end of the
Mm-hmm.
one that has the S in it.
Yeah. Working through the data structure. All right, so here's our root. Here's the A, points to a child. B points to a child. C points down here, and there's the end of string. Okay, so a couple of things. We have to mark end of string down here. If we marked an end of string up here, we know that our word starts with an A and is followed by a B, but we don't know that the C is somehow significant. Okay, so we need to follow the C to another node, and in that node we mark the end of string. Okay, so let's answer Travis's question. Let's insert an AB into the try.
Oh, I screwed up.
Uh-oh. Memory fault. And so what changes for an AB?
You add an end of string on the same node as the C.
Yeah, so right here, you put an end of string bit to 1 at that point. That says A followed by B. That's a word in the try. Okay, so let's add the word W. W. That's a new word. I just made it up. So remember, when you're adding these, your root never changes. Okay, we're always going to start our insert or our search from the root, which in this case is this node at the top. And more often than not, we'll end up going to a new node, unless we're going somewhere that, you know, is part of something we've already formed. Yes, you want to run to a new node. Yeah, yeah. And then just the other string on that one. So here's your root node. So you might want to do that. Yeah, but this is technically So if W pointed here, if you set your end file here, that's actually saying that there's an A stored in our structure.
Oh, okay, so
Yeah, get rid of it. So you can't get rid of that, so you want W phone to come down to here. And then hit the end.
I didn't even hear it. I didn't.
So the end string right here, is also saying that there's an A in your structure, because if I call up an A, that'll hit. So the W phone wants to come down to a new node, and then hit the end string on that one. All right, so getting the idea. So if you put another word in like T, let me fill in my W. So another word like T, that's going to be the same as W, right? You're going to have to come down to a new node. And hit end of string. And then how about THE? So the things coming off of a letter, they always point to a node, not to a letter in the node, right? You're just pointing to the beginning of that whole node. So if the T comes down here, you put that to a 1, to indicate the letter T. Yeah. And then, yeah, exactly. Then what we'll do is just set that up. That should be set to a 1 for letter T. Then, since you already have a T coming down here, you just come off of this stage.
Most of this guy points to the end of it.
T, T, H, E.
Wait, what?
Yeah, yeah.
They're all pointing to the end.
Yeah. Oh, yeah, I know. This one was too busy. The other one.
T by itself would come down here at 8, that would be 1. That would be 1. So then, from that point, I can rank to the H, or the, yeah, perfect. Right, that's a T. H, E, that's it, that's that. Yeah, it's just a flag. Yep. And then for the letter T itself, is that good to be a 1? And store the T. So we can't point to 2 different nodes, right? So this was correct for storing the letter T, so it would actually come off of that that H down there. Yeah, so that's the other thing. Each thing that we point to, we can only point to one thing from a letter. Right? We can't point to multiple ones, but you shouldn't have to point to multiple ones. You can always reuse. You got T, H, E, good.
This is like a lot of spaces taken up.
Say again?
This is like a lot of spaces
It
taken
is, yeah. Good thing you got a computer. Mhm. Yeah, so this is T in there. Okay, then H points to E, and then E should come down somewhere else. And that should be where EOS is set. That's the end of the dot, right? So this is actually saying TH and then your structure. Yeah. Cool. You got it. And then to store T itself, just put a 1 right there. Cool.
I say make them put you in certain spots, but it's just on the side.
Okay, okay, yeah.
Just like,
So T, H, E. Alright, okay, so that would be a 1 to store the T, and that would be a 1 to store THE. Cool. I like that red works. They're pink. Excellent. And there's your THE, perfect, got it. Okay. So for THE, you,
That's from
oh, that's from the T. Okay, got it. So it's still H. Okay, perfect.
No.
No. All right, cool. Got the idea?
Yeah.
That's all there is to tries. It's probably an exam question, so if you can do what you did here, you got points. So yeah, space-wise is really bad. The nodes are wide, and you need a lot of nodes, right? Anytime you have a unique sequence of letters, you have that many nodes, however many letters there are in that word. So as you start to put more and more stuff in, you start getting overlap, you begin to reuse these nodes. But you know, a lot of times we have all of this space and we've just got a single pointer coming off of it or a single bit set, right? So not very efficient, but really fast to work through. All right, so questions about that? All right, well, that's it for tries. That is the end of that lecture. All right, well, let's start talking about sorting then. So sorting is a classic problem in computer science, and I'll pick on integers mostly. All right, so there's 8 integers, and they're stored in somewhere in memory. They could be in an array, thanks, or a list or something. Or sometimes they're just being input from outside. And we want to put them in increasing order, or decreasing order. And there's a variety of ways to do this. So some of the things we're going to talk about will review a bubble sort. An insertion sort, a selection sort, merge sort. I'll put sort here. Something called a quick sort, written by someone with a marketing angle. Radix sort. Not the same person who invented complex numbers. It was not a marketing. Radix sort, heap sort, and we may do a few others, topological sort, if we have time. There's lots of different ways to sort stuff. Right? Why do we have so many different ways? So I think I've told you before, really the only thing I've ever coded outside of the classroom was a bubble sort. That Google challenge that I got that popped up and I had to do some sorting in there, I did a bubble sort. Right? It's inefficient, but it's, you know, generally fast enough, unless your whole life is sorting. Right? If you're a database engine who's trying to present query results all day long, right, you might not want to be doing a bubble sort. So we'll be looking at how efficient these things are, order of complexity. And remember, order of complexity, this big O notation, is not really looking at how long does a sort take. We're not interested in just the raw clock time that's consumed to do a sort. We're interested in how does the sort time change as the amount of data changes. So if you give me twice as many things to sort, is it going to take twice as long? Is it going to take worse than that? And so bubble sort, insertion sort, selection sort, these are all order n squared. Really bad performance. So if you double the amount of data, it takes 4 times as long. If you have 10 times as much data, it takes 100 times as long. And if you have 1,000,000 times as much data, it takes 1,000,000,000,000 times as long. So you go from 1 second to 1,000,000,000,000 seconds. That's really bad, okay? Merge sort, quick sort. These get more like n log n. And that's good. It's not quite as good as order n, which is linear, but the disturbance from being linear is pretty nominal. Right? If you got 1 billion things, log n is around 20, so 20n, that's not bad. Heap sort, depending on how we measure it, is, I believe, also n log n. Radix sort is an interesting one. In some ways, radix sort is almost like order 1. We're generally going to call it order n, which seems better than all the other sorts. Right? It really just depends on how many pieces of data you have. And it's a quirky sort because we're sorting our numbers as if they were just characters, just strings. And we just look at the digits and we order things based on the digits. And we can do it as order n. Well, let's talk about these order of complexities a little more, because there's some subtleties here. And when you get to an algorithms course, you'll spend a lot of time talking about this big O notation and little o and theta and all these other ways of measuring performance. But I want to give you a little better intuitive idea. So size of data, time. So let's just imagine some algorithm that when you have 2 pieces of data, it takes, I don't know, 1 unit of time. And when you have 4 pieces of data, it takes you 4 units of time. And when you have 10 pieces of data, it takes you 25 units of time. So the effect here is when you multiply the size of the data by 2, you multiply the time by 2 squared. When you multiply the amount of data by 5, you multiply the time by 5 squared. Okay, so this is order n squared. So suppose next year we've got a computer that's 10 times as fast. And so to sort 2 pieces of data only takes 0.1 seconds. And to sort 4 pieces of data now takes 0.4. And to sort 10 pieces of data now takes only 2.5 seconds, or whatever our unit of time is. Right, this computer is a lot faster. It's taking 1/10 the time to do stuff. The clock speed went up by 10x. But the growth in time complexity is still the same. When we double the amount of data, we quadruple the amount of time. When we increase the data by 5x, the amount of time increased by 25, 5 squared. So this is still order n squared. And so this order of complexity is kind of impervious to linear scaling. So if I have a different algorithm that you know, I'm going to code this up in some other language or some other version of the algorithm, and I have to do twice as many steps, right? So this will become 2, and this will become 8, and this will become 50, right? You can probably pretty easily see this is still going to look like order of n squared. Right, doing twice as many things inside doesn't really change how this scaling behaves relative to scaling the amount of data. So here's what's going on. Let's look at a basic bubble sort. So there's a pseudocode bubble sort. We make one pass through our data, and we compare each piece of data to the piece of data after it, or before it, and we check to see if they're out of order, and if they are, we swap them. And after one pass through our data, our largest piece of data is in the bottom position of the array. And we make a total of n passes through our array, and each pass, another piece of data goes into the correct location, and so that ends up putting the whole array in order. So the critical part is really this nested loop. Right? This stuff inside here is going to happen n squared times, because we're going to go through this inner loop n times, and each of those inner loops is going to happen n times. So this stuff inside is going to happen n squared times. And there's 2 situations. It may be that every time we compare 2 pieces of data, we find they're out of order and we have to swap them. Or it may be that every time we compare 2 pieces of data, they're in the correct order and we don't have to swap them. So the amount of time required for this inner piece can change a lot. It may be just a comparison, or maybe a comparison followed by a swap, which is, you know, these 3 assignment statements and such. But that is equivalent to just some linear scaling on the actual amount of time that's required. The way this problem grows in time as n increases is still going to be n squared. So when we're analyzing algorithms and computing these orders of complexity, we get to do a lot of sloppy things. like throw away constants, right? They won't affect us. Similarly, this is going to go n squared times, right, which is n plus n plus n, total of n times. But if we write a little more clever bubble sort, we know that each time we go through one of these passes, the last element of the array is going to be in the correct position. So each time we go through, we really only have to go from j equals 1 to maybe something like n minus I. Because once we've gone through 5 passes, we know the last 5 elements of the array are in the correct position. We don't need to go through those 5 and see if they're in the right order. So this will actually take something like n plus n minus 1 plus n minus 2, right? Something like that number of iterations, which is something like n times n plus 1 over 2. So it looks like instead of order n squared, it should be order n squared over 2 plus n over 2. That's really no different. So order of n squared over 2 is the same as order of n squared. That's just, you know, another scaling. Here we've got, you know, n divided by 10. It's still order n squared. And let's look at one more. It's the size of data. That's n. Let's look at n squared plus n. So n is 1, n squared plus n is 2. N is 10, n squared plus n is 110. N is 1,000,000. This is this number. So as we go from 1 to 10, this increased from 2 to 110. So this was about 55x. If it was order n squared, we would have expected 100x. Again, when we go from 1 to 1,000,000, we expect this to be about 1 trillion x. This is half a trillion x. Okay, minus a little bit extra over here. But if you compare this to this, right, which went up by 100,000, that ratio of n squared plus n is really close to 100,000. So I don't want to go calculus on you. I'm not going to go calculus on you. Because I'll write something that's not true. But we're looking at a limit, okay? We're looking at as n gets very, very large, right, approaching infinity. How is this increase in, for example, n squared plus n relative to n? What does that look like? Okay, and it's going to end up that in the limit n squared plus n is going to be the same as just n squared. So first order approximation, when we're doing big O's, we get to sweep a lot of details under the rug. Okay, now your algorithms teacher would freak out. But first order approximation, right? We're looking for what's the dominant factor that's describing how much the problem time increases as the data increases, and it's dominated by the highest power here, n squared. If we have n log n or we have 2n log n, it's going to be the same as log n. Now log of n squared is going to be different from log of n. N squared log n will be different from n log n. Okay, but we can push the constants around. And there's worse things than n squared. You know, there's certainly order n cubed. If you start dealing with higher dimensional matrices, you find lots of n cubed operations. But there's things far worse. There's n factorial. There's n to the n. And a lot of graph theory problems will have simple solutions that are order n factorial or n to the n. Right? So n to the n means that, you know, you have n pieces of data, there's n ways to explore the solution space at each of those points. So when we were dealing with recursive algorithms, these kinds of orders of complexity can start to pop up pretty easily. And that's one place where dynamic programming is kicking in, because it's letting us avoid rechecking certain cases. So here's a classic problem. So some sort of fully connected graph. And these are cities, and you have distances between each. And your question is, starting at one place, what's the path you should take so that you can visit each city and return to your original point in the least total distance? Okay, so this is the traveling salesperson problem. And it's probably the most attempted computer science problem out there. People who have no background in computer science will spend their lives trying to solve this. It's a very famous problem. It's easy to solve if you don't care about efficiency, right? If you start here, if you have n plus 1 cities, from this point you have n possible places you can visit. And once you visited one of those, you have n other possible places you can visit. And once you visited that, you have n other places you can choose to visit, right? And you're allowed to go back to a city you've already visited. And if you have a total of n cities, right, you have on the order of n to the nth possibilities. Well, you write n nested for loops, and you can find how long it takes from here to get to every city and come back. And you just run it over those n nested for loops, and you take the smallest answer. But that's a lot of computation.
Can you do it recursively too?
Yeah, you can do it recursively, definitely.
Does that cut down on efficiency?
Not horribly, but it's still going to be n to the n probably, unless you start getting nuanced. All right, so we will start talking more about sorts tomorrow.